Of course, we will be applying these boundary conditions. It will be clear to you. So what we are trying to do is now we are trying to represent the stress matrix and relate it to the strain via a certain matrix. We call it a D matrix, which we call it as a stress strain matrix, yeah, because it relates the stressors to the strains. We can also call it a constitutive matrix. We can call it a constitutive matrix, this D matrix. Just try to keep in mind the important steps, the flow of this derivation. That is what is important. Okay, I'm not trying to just show the stiffness matrix directly for a let's say plane stress or for a 2D element, because it's good to know as to how these equations or these matrices are derived, that you will have certain confidence when you're tackling problems, or this is not fallen from the sky. This had a certain basis for deriving. So we call the matrix which relates the stressors to the corresponding strains, we call it a stress strain matrix. Of course, quite intuitive as the name indicates, and we can also call it a constitutive matrix, which is nothing but a matrix which includes material properties. What are the material properties? The module of elasticity and of course the Poisson's ratio. So this nu includes the Poisson's ratio, E defines the material of elasticity, and the D matrix can be derived. I will not go into this derivation. If you are really interested, you can refer, of course, in the references how this constitutive matrix is derived. But it's okay for you to know that this constitutive matrix relates the material properties, or it relates the stresses to strains and includes material properties. So if we consider the plane strain condition, we know the strains acting in the Z direction, and of course the rotational strains, or the shear strains in the X, Y, and Y, Z directions are 0. Yeah. So the three-dimensional, let's say, for the three-dimensional stress strain relationship, where this condition is satisfied, where the normal stresses is not equal to 0, this is of course for the plane strain condition, the constitutive matrix will have this form. For the plane stress conditions, we will have it in this form. Of course, for the plane strain condition, we will have it in the other form. Here. So only a slight difference between these two terms, depending on the nature of the problem that we are going to tackle. So depending on whether we are tackling a plane stress problem or plane strain problem, the D matrix will vary. The constitutive matrix will vary. Yes. So what is the next step? We have found the relationship between the stresses and strains. Yeah. If we further consider the plane stress case, what do we know in the plane stress case? We know that the corresponding, let's say, stress matrix and of course the strain matrix, they are kept intact, or they remain the same for a plane stress conditions. So for a basic, if we can consider basic partial differential equation considering the plane stress case. Yeah, so I will, yeah, for the plane stress case, if you consider take these equations. So you have to either refer it to a reference or you have to take my word on this. In this case, you can take my word on this, of course, and when you're interested, you can go and refer as to how these derivations are done. In the plane stress case can be characterized using differential equations, which relates, of course, the strains, of course, and of course in the y directions as well as the normal directions. And of course you can see the material Poisson's ratio has come into to the equation. So imagine these two set of equations are used or can be characterized to define a plane stress condition. Okay, so we will be needing these cases. That is why I just mentioned beforehand. So sometimes you might be wondering also how these things jumped up all of a sudden. So it's okay for you to assume that these equations are used to characterize plane stress and plane stress conditions. And when we derive this the stiffness matrix for a constant strain triangular element, we will be using these equations. Yeah, so now let's come to somewhat an interesting part. What we are interested is at this moment is to derive the stiffness matrix for a constant strain triangular element. Yeah, so we know our interest is to analyze a component like this, a thin plate which is subjected to traction or tension, and we would like to perform a finite element analysis of this thin plate in 2 dimensions. So we have come up with the displacement functions in the x and y direction as u and v. U in x direction, whatever the displacement in x direction, we define it by the function u. Whatever displacement in y direction, we define it by function v. Then we are now trying to discretize this problem by considering small triangular elements or finite triangular element. We call it constant strain triangular elements because the strain along this throughout this element is constant. Yeah, so this is the simplest form that we can consider, and you can see that total element has been broken into small triangular elements. Of course, you can see the compatibility conditions. They are connected along edges. There are common edges for certain elements, of course common nodes which are connected to other elements. This is the discretized form. So just like we did in the previous sessions, when we derived the stiffness matrices for the springs, for the trusses, for the beams, we followed certain steps here. We followed 7 odd steps when we derived the stiffness matrices. So let's apply. It is the same concept that we apply here also. Let's go through these 7 steps to derive the stiffness matrix. The first, for a constant strain triangular element, the first step is, of course, to select an element. What is the element type we consider? We have considered a triangular element to be the most fundamental element when we perform this analysis. Yeah. So in order to define this triangular element, we have used, so this the plane element or the 2D element, we have used 3 nodes given by I, J, and M. Mind you, the clockwise notation here we use, let's say, the counterclockwise notation when we are labeling the the nodes. It is important when the problems get complex. It's easy to understand and easy to tackle the problems when you have a certain convention. So the convention here we use is that we use a clockwise, we go in clockwise when labeling the nodes. Of course, we go counterclockwise when we are labeling the nodes. Of course, if one needs, you can use a clockwise formation, but it is important that it has to be consistent with the other notation that we use when we are deriving the elemental equation. So we stick to one sign convention. Yeah. So we consider when we are when we're labeling the nodes, we go in the counterclockwise direction. That's why we have moved from we have named the three nodes I, J, and M. So what we yes, for each node, you can see the displacement functions. The displacement components of each node is written as of each node in the x direction, as well as the displacement components in the x direction and y directions are written using u and v. So the displacement of the ith node in the x direction is ui. The displacement of the ith node in the v direction in the y direction is vi. Similarly, other nodes, the other notation of or the displacements of the other nodes. Yeah, u and v corresponding to, and the subscript is defines the node, and u and v defines the direction. And what else do we know? We also know the coordinates, yeah, of these nodes, I, J, and M. So what are the coordinates of I? Let's call it I, comma, yi defines the coordinate of the ith node. Xj, comma, yj defines the coordinates of jth node, and similarly the mth node is given by xm dA. So we have placed all the corresponding necessary notations to describe the displacements of each node in x direction and y direction, as well as the nodal coordinates of I, J, and M. And of course, we have used the counterclockwise notation when we are trying to define the triangular element. Then the next step is we have to define a displacement function. Why are we interested in displacement function? Because we know when we are deriving a stiffness matrix, we are trying to now express the forces or the stresses applied in this on this component using the nodal degrees of freedom. And the nodal degrees of freedoms are defined by the displacements of the corresponding nodes. For this, we defined a nodal displacement matrix D, which has two segments, three components. What are the three components? Displacement in the ith node, jth node, and the mth node. And each node has two segments. In x direction, I node has the displacement in x direction and y direction. Similarly for j and m. So there are 6 elements in this column matrix. Good. Now we have selected the element in consideration, and we have defined a notation to define the displacement function of each node. Quite clear. Nothing new we have done. In the next step, as in the usual case, we have to make an assumption. What would be a good displacement function which can be used to describe the displacements of each node? Okay, so the simplest case to start with, and of course, when we talk about, let's say, compatibility conditions, because when we are talking about a line, if we consider 2 points, because we know in this element where we have 3 nodes, if we consider 2 nodes, they are connected by a line. So if we define a line, if we define two nodes, can be easily characterized by a line. And when we are considering compatibility conditions, it would be really easy if we use a linear function to characterize the displacement of each node. It will be quite handy or useful when we are, because when we are imposing compatibility conditions, if we come up with a linear function. Okay, because we are considering displacements along the edge and as well as nodes shared by other elements. So if it is a linear function, this is quite useful when we are talking about when we want to analyze the subordinate or the element which is next to the, which is connected to the current element that we are talking about. So linear function is the most let's say the most elegant way of achieving compatibility conditions, as well as when we are talking about common edges, it's the most easier convenient function to be used. So keeping that in mind, let's use a linear function, and whatever the displacements in the, let's say, x directions, yeah, let's characterize it by the, it is characterized by u function and can be expressed in using coordinate system, of course, using linear functions defined. Now we are talking about the 2D system. Of course, we have x and y coordinates, and we have, of course, certain exponents, and this xy, this equation defines a linear equation. Similarly, whatever the displacement in the v direction, y direction also can be characterized by using a linear function. So now we can write down the general displacement functions using the displacement functions defined in the x direction and y direction, and express this general, the so-called general displacement function using these two equation 5.2.2, and let's try to simply separate the coordinates with the exponents. Yeah, so we have simply these two equations describing the displacement in the x and y direction, and what we do is we simply take out the exponents which we like to find now. X, a1, a2, a3, a4, and s up to a6 are unknowns. We would like to find these unknowns for each node, and x, y are the coordinates which we already know. So we arrange this, nothing new. We have arranged these two displacement functions, or let's call it a general displacement function matrix, in the form of, we have arranged it in the form of matrix. Now what we are interested is, as I mentioned before, is to find these a values, because these are constants which we would like to find. So what to do this, what we do is we simply apply the, let's say, coordinates. Yeah, how? We simply consider the u function, and let's consider I node, and let's write down the displacement of the ith node in the x direction, which is given by the u1 ui function. And so we know this is a function of x and y coordinates. So you simply plug these values, the x and y coordinates, into this equation, into the u equation here. So, and you would obtain the exponents a1, a2, and a3, or we can describe the exponent, the function using a1, a2, and a3 exponent. Similarly, you can write the displacement function for the jth node and the mth node. What you have to do is you simply substitute the corresponding nodal coordinates. You would end up in getting three elegant equations. Yeah, if you know if you have three equations, then you will be able to find the corresponding a values. A1, a2, and a3 can be found now. So we also know that there's a displacement not only in x direction, also in y direction for the three nodes. Let's also define them. So the function v describes the displacement in the y direction, and I, j, and m corresponds to the three nodes. You simply substitute the nodal coordinates of that is corresponding to I, corresponding to j, and corresponding to m, and you would also again get another set of equations, three equations characterized using A4 and A5 and A6 constants, which you can find out by solving this simultaneous set of equations. Quite straightforward, nothing new. So we take the first three equations, we try to solve, or we try to obtain the A values. The U values are given in terms of A1 and A2. You separate these three equations. So basically you have considered this first set of equation, first three equations, and you have separated the variables, separated the constants, and written down in the form of a matrix. So in order to find the A values here, what do we have to do? We have to take the inverse. In order to find the A value here, you need to take the inverse of the, multiply with the inverse of this matrix. Let's call this matrix X. Yeah, if this is the X matrix, you have to multiply it with the X inverse in order to find the A value. So on the left hand side also, this has to be multiplied using the X inverse matrix. So is there a possible way of finding this X inverse matrix? This is the X matrix. Is there a possible way of finding the X matrix? Yes, there is. A method of cofactors can be used to find this X inverse of X. Yeah. If you are interested, of course, you can revise. Maybe you have learned this method. How you, if you are given a matrix like this, how you can find the inverse of such a matrix. You can, since we have a lot to cover, of course, if you're interested, you can go and do a search and to find how these cofactors can be used to find the inverse of such a matrix. I will simply write down the answer so that for the sake of continuity of this lesson. So you can use the method of, let's say, the cofactors, the method of cofactors. You can use the method of cofactors to find the inverse of X value. You can see it is defined using 1 over 2a, and there's some kind of, let's say, another set of terms given by alpha, beta, and gamma has been included in this equation 5.2.7. We will look as to what they mean really. And A corresponds to now the area of the triangle. Yeah, A corresponds to, check with the, yeah, A corresponds to the area of the triangle that we are considering. Yeah, so how when we defined the inverse of the matrix using the area and these terms alpha, beta, and gamma, which corresponds to I, j, and m nodes, we already know this value area, of course. Then we know a two-way value, and the area, of course, can be obtained. How? By simply obtaining the determinant of this matrix X. If we obtain the determinant of X, we will end up in getting the area, corresponding area for the element. So if we solve this equation 5.2.8, this is nothing but this equation. We have obtained the determinant of this equation, which gives us access to the area of the element. So you know how to find the determinant of the material of this matrix. If you expand this, or if you try to find the determinant, you will, if you further simplify it, you will end up in getting the relationship given by equation 5.2.9, and you will be able to easily calculate the area of the triangle. Okay, now we know the area of the triangle. Next, let's see what this alpha, beta, and gamma, what these components are. These are nothing but, let's say, for the clarity, since our matrix, when we use the method of cofactors and obtain the matrix, since it gets elongated, convenience, we have used certain definitions given by alpha, beta, and gamma, and corresponding node has been used. Alpha, beta, and gamma is nothing but these terms as given here. Yeah, so alpha is a function or a value. Basically, it's a value. Yeah, it's coefficient, because x, I, y, m, and these are nodal coordinates. So using these different nodal coordinates, you can obtain these coefficients or constants. Yeah, for example, the b only corresponds to the y coordinate, and the gamma corresponds only to the x coordinate. So there's a pattern. So in order to simplify this inverse of the matrix, I have used this sign convention, or let's say these definitions. Okay, we have now obtained, let's say, the area, good, which is required to find for obtaining the inverse by obtaining the determinant of that matrix, and we know the nodal coordinates, so thereby we can obtain the alpha, beta, and gamma values corresponding to the three ij and m nodes. So now our aim is to find the coefficients a1, a2, and a3. Yeah, so we simply multiply, let the x, okay, we take the x inverse, because we already know this x inverse now, the value of x inverse. We can simply substitute here. X inverse is nothing but 1 over 2a, and given by alpha, beta, and gamma here, should be multiplied by the displacement function in the x, y, of course, corresponding to the x direction, and by taking into account the three nodes. Similarly, how can we find the other three, let's say, components corresponding to displacements in the y direction, that is a4, a5, and a6? You simply write down. Similarly, you have to follow the same procedure. a4, a5, and a6 can be obtained by obtaining the determinant of the matrix, the x inverse matrix, the determinant of the x matrix. You will be able to find the area, and of course this part comes from the x inverse matrix, and the corresponding parts here, which defines the displacement in the y direction for the three nodes, are given.